Okay, so let me show how you configure parameter for each block. So first you have the input signal as a pulse. So in this pulse, the amplitude is 1, means when you fully turn on, the input level of the voltage is 1. And of course when you turn off, you switch off the K, it will completely turn off, so it drop to 0. And this is the period of a full a set of switch on and off. Okay, it's 10 milliseconds. And the percentage of the duty cycle is 50. And now we don't need to consider any phase delay. Then this one is I use this block because next time I will add noise to this, but now there's no noise. And this transfer function, I think it's easy to configure. Smart merge also easy. For this one, we will just see the period. The curve will show it between 0 to 0.5 seconds. And the last one is this one, the time that we need the number of points at every sample time. So here we use a period 0.001 for like a sample time, like a number of points that we want the scope to display. Initialization time, I think this one can be 0. Let me try. I need to delete this one first. Yeah, I need to close it first, and then yeah. So it's okay if we start from 0, then how do I zoom it? Zoom this and then zoom this. Yeah, this one from 0 to 1 here. Yeah. So initialization 0, it means at what time you start. So we start from 0. Yeah, we are supposed to start from 0. Okay. Now let's observe what is the final value. So here you can see the transient up to here, and then you got the steady state. Then the final value is about 0.5. Why 0.5? So let's say if you use the percentage here up to 75%, then here you can see that the level at the steady state go up to 75%. Okay? And if you lower the percentage of this one down to 25%, and when you run it, you can see that the value of the filter signal is around 0.25, which is 25%. So this is the way that we can varying the value of input, okay, by using pulse at high frequency. This one is called pulse width modulation. So like I explained before in the lecture, we can use pulse width modulation to vary the value of input. We only implement switch, okay, to switch on and off at a very high frequency. So we don't need to use any special amplifier that can amplify at a certain range of voltage. We only deal with, we only use the advantage from the switch just on and off at high frequency. Then we can get any level of the input voltage, okay? And what happens if we have noise? Oh, by the way, let me show another type of input, which is step. Let's take step function, and let's say you give the step as 25% and see the graph. How does it? Okay, what? Maybe I should copy. I don't have the mouse. I should copy. It's not easy to copy. Let me copy all of this. Control C and then Control V. Let's say I use step for this one. And for this step, I also use step from 0, and the final is 0.25, let's say. And let's see the result of these two. What does it say? Block is ignored because of undefined input. Undefined input, why? Initial value, step time, initial value 0, step time at 0, and final value at 0.25. No. Everything should be same. Time. Undefined input. Undefined input. This one is undefined. Why undefined? Step. Initial value 0, final value is here. Step time at 0. Just try this one. Oh, what happened? And I did this again. Yeah. Okay. Okay. Maybe it's easier to see if I use this one's 75%. Okay, 0.75. And this one also 75%. Where is the percentage here? Okay, and then look at the result of these two. I can see only one graph, so I use a different graph. This one, this one. I need to use other block, things, and this scope. Okay, and run again. Okay. So you need to use one scope with multiple port, and you need to configure the port like this. Yeah. So port number one, you have two signals because you have mux here, 1, 2, and the second signal from here you also have 2. That's why you need to use 2 like this. Okay, mean and max you set define like this. Refresh period again 0.5, 0.5, and then you can get graph like this. Okay. So look at these two graphs. You can clearly see that the response of the first one and the second one is actually same, right? Are the same, almost same, because this one you have like a little fluctuation, right? So in some sense, it's kind of you give the input to the system as 0.75 volts, just like this one. But you do a different way. You just switch on and off. And this is how we use to control DC motor or even other type of motor. We use PWM technology like this. And so can you get the same result? Okay, suppose I want to see the effect of noise, so I connect random generator to this add block. Same for this one, and here's how I configure the input parameter for the random generator. Data type 1 is real, so real here, So put 1 to get real. Flag don't need to change, don't need to care. A, B, A is mean value. I think it's gonna tell us here, right? A is, okay, if the flag is 1, okay, flag is 1 here, it means normal distribution, right? Normal distribution. So I choose 1, and the meaning of A is mean value and B is deviation. So I use 0 mean and deviation as 0.1. Deviation means the square root of variance. Okay? For the seed, you don't need to change. Usually the default is a very large number, but large number is good. Okay, this one. Don't start from 0, 1, 2, 3. It's not good. Okay, so just use default for seed. And yeah, then simulate our system again. Let me close this one first. Let me simulate it again. Yeah, so now the input 0.75 volts, but corrupted by some noise. But then you can see that the response somehow is smooth, right? Somehow it's much smoother than the input, because high frequency noise is filtered out. Okay, and this one, the corrupted noise doesn't seem affect so much on this, right? Let me show you the parameter for the random generator again. So next we are going to discuss about second order as low pass filter as well. And so we're going to build a second order system and simulate with different inputs just like before. So here is the transfer function for second order system, and we write in terms of zeta and omega n like this, and let's choose zeta 0.4 and omega n as 2 pi times omega n should be, I think omega n should be small. Omega n should be small. Yeah, should be small. So this one, so omega n should be small. Let's say omega n equal to, yeah, let's try omega n equal to 0.1 first. Okay, zeta 0.4 or any value less than 1, but yeah, between 0.4 to 0.8 maybe it's good to see the overshoot. And so let me go to this one, and I try zeta equal to 0.4 here, just to get the value in the workspace here, okay, or variable browser. And then omega n equal to 2 pi, no, yeah, it depends on how we define it in terms of frequency, right? So maybe, yeah, just say 2 times pi times, let's say just 1, oh no, 0 point, maybe 0.0. Well, I just said that I want to try it with 0.1. Yeah, should be small. Yeah, just try with this first. Okay, now I have values at 9 omega and here, and then I can define another. Okay, I'll just copy. No, maybe I just change one of them here. So let's change transfer function this one. Just keep this one as first order, and this one is second order. Now I define it as like this. So I have s square plus 2 times zeta times omega n, and then plus time s, and then plus omega n square. Also for the numerator, omega n square, right? Yep. Okay. Yep. And now I only consider the filter that we have pulse as input for first order and second order, like this. Okay. Then I can run it. And here it seems this is not right. Omega n square. I should have omega n should be large or should be small in this case. Omega n now it's natural. Omega n, I guess omega n should be large. Yeah, omega n should be large. That's my mistake. So omega n equal to, let's say 2 times pi times 50 undefined variable pi. Oh, I see. So 3.1415. Okay. Now I change omega n and I run this one again. Yes, omega n somehow is too big. Well, so for the second order, it's a little bit difficult to find, to design it. Yeah, I would say. Okay, let's say just 50. Let's say just 50. Let me close the graphic first and run again. Okay, this seems good. So we can see that the output, the final value of output seems to be the same for both cases, right? So first order, second order behave like first a low pass filter, but you need to choose the right damping ratio and frequency, natural frequency. So here I choose 50. To be 50. Actually, there are methods to design filter. low pass filter, band pass filter, or high pass filter. But it's out of the scope that I need to teach, so I only just trial and error and see the result. Okay. So you try by yourself how to configure the parameter. Actually, here I use same pulse. We also still use noise, and then this is can order omega n is 50, zeta is 0.4. Okay. Okay. Let's see if zeta a little bit better, bigger. Let's say zeta equal to 0.8. Then let's see the result again. Let's overshoot. So these two look much like the same, right? These two results look much like the same. And now you try by yourself. And then next, we already complete this one. And then, okay, let's see another problem. Okay, practice number 2, velocity control. So again, here we can use property of first order and second order differential equation to design controller for systems such as DC motor. Suppose we can measure omega, which is angular velocity here, and then we use feedback from the measure value. We compute the difference from the desired. Okay, desired means you want it to rotate at this value, and then you can measure and you compare the two, then you get the error, right? And then you use PI controller here to calculate which amount of voltage should be supplied to the motor. Then finally you will get omega actual become the same as the desired, or we can say that the error tends to 0. This is what we want. Okay. Then we need to find a way to choose the right coefficient of PI controller, Kp and Ki, right? So here block diagram that use Laplace transform. Okay, this is a plan for the system. Input as voltage, output as angular velocity, and I will use this kind of notation, which is much easier for you when you derive to find coefficient of controller. Okay? I'm going to explain briefly here. So the original equation for the DC motor as a first order, because we ignore inductor value, we ignore the inductance because usually it's very, very small. And so here output is omega, input is voltage U or VA, same, VA here. And so when we design a PI controller, Kp and Ki like this, then we compute U. Yeah, we formulate U equal to Kp times error, okay? Kp times this error plus Ki times integral of error. So the inside here is error, okay? And then plus compensation. Compensation, why need compensation? Because actually I imagine that if I can derive equation of error in the like to be like this. If I can derive error to be like this, say let's say if second order error omega plus some coefficient, let's call it k1 e dot omega plus some coefficient k2 e omega equal to 0, I can say that this error will asymptotically approach to 0 when t go to infinity, right? So I choose the controller a PI like this, but when I substitute it into the dynamic equation, I don't feel that I'm going to get 0 on the right hand side. Perhaps I need some compensation to cancel out the right hand side to be 0. This is the idea, right? Choose PI and then compensation. So substitute u into this equation, u here, and you derive, okay, to get errors like this. So let's say you have only omega dot, then you need omega d dot. You need minus omega d dot. Then you just minus it. And you also minus it on the right hand side, something like that. So by this kind of manipulation, finally you can find compensation to be like this. And you can choose ki, kp in terms of omega and zeta of the second order standard form. Okay? So well, actually, when I derive equation to get equation like this, and then I compare to the standard form like this, zeta omega n e dot omega plus omega n square e omega equal to 0. Compare it. And inside this k2 and k1, k1 and k2 are function of kp and ki. Okay, kp and ki. So by comparing these two coefficients, the coefficient of these two equations, you can easily find ki and kp. Okay, and for the compensation, you can find it by trying to cancel out the right hand side. Okay. So finally, you get this architecture for velocity control. And so now we can build a control system for this architecture in ITC-DCLab. It's gonna be quick. I think I already have, I guess, velocity control. Continuous system. I hope I have it. No, I don't have it yet. Okay, so let's build a new one. Control N. I think I need transfer function. Transfer function is just b over a, right? B over s plus a, sorry, s plus a. Oh, very unfortunate for this. We need to find a and b first. Let's say a equal to 30 and b equal to 20. Then you can choose b here and s plus a here. Okay? And then you need sum. And how about controller? Controller you need gain, right? And from sum you need you have controller in between. So I go to block here and go to should be mathematical operation. So I need gain. Where can I have gain? Maybe just this one. Gain. Why so many gain? Just try one. I will need two. No, actually I need four. Why I need four? Because this one is Ki, Kp. Yeah, so I need to write down Ki and Kp. So here formulation of Ki, Kp. Okay, here. So I need omega n, but now omega n I need to choose not for the previous example. Omega n here should be around 2 times 2 pi. Okay, 14, 15, and time just 5. Okay, and zeta equal to just 1 in this case. Or 0.8 is fine as well. Yeah, 0.8 is still fine. So let's use it. And then Ki equal to omega n square divided by b, right? Enter. And then Kp equal to 2 times zeta times omega n minus a, all divided by b. Okay. So I go back to ITC-DCLab course, and here I want to use Ki, and here I want to use Kp, a little bit bigger. Kp, and for Ki I need integrator, so I go there to get integrator in continuous time, integrator here, integrate first, time coefficient later. And then I need some, also some, yeah, I need some here, but I need 4 port, okay, like this. Why? Because I need here from compensation, right? So okay, I connect here first, and for compensation, let me show the slide again. Compensation is 1 over b omega d dot 1 over b and a over b, okay? So 1 over b, 1 over b, and this one is a over b, okay? So a over b times omega d. So let's say this is omega d, right? Cannot. So omega d. Let's say I have a sine function. Let's say I have sine function. This one. let's say this one is omega d dot, and then I need integrator. I need integrator to get omega d. Okay. I need integrator to get omega d. So here just omega d dot. So omega d dot times 1 over b. So omega d dot is here. And omega d times a over b here. Okay. And then I add to here as well. Okay. This one should be minus, right? Should be minus. So this one is input, this is output, and then I get feedback to compare with the desired. And then I need scope. Oh, not the scope, but other scope. Go to sync and then scope. So I like this. Right click, link style, optimal. Optimal, not really optimal. Okay, and clock this one. Okay, so I explain again the concept. First, you have dynamic system. You have input VA, and output is supposed to be omega. You need this omega to feedback, so you need this sum. Okay. So 1 plus 1 minus, and here is omega d. So forget this for the moment. Just know that the input to the sum here, omega d, and then the output of this comparison is error. From this error, you pass through PI controller. So this is P controller. This one is integrator controller, right? And you need also compensation. You need omega d. Omega d here times A over B. Where is it? It's here. Omega d times A over B and plus omega d dot times 1 over B. Okay. See omega d here times A over B, and here before integrator it's supposed to be omega d dot, right? Because omega d dot integrate and then you get omega d. So here omega d dot times 1 over B, right? And then I change the scope a little bit. Oh, this one is 50 seconds. The value 30, 20. Yes. You need to compute it from this formulation. Ki omega n square over b, kp, this one, a little bit smaller. How can I enlarge the font? You want to see it again? Okay, I think I want to see the scope of error as well. Yeah, maybe it's more interesting to see error. But okay, let's say first let's see this one. Oh, but by the way, I need comparison, so I want to see. Yeah, I think output port window position. I think I should use a different scope. It's better to use this one. Yeah, and so this one, but need to configure a little bit. Each port just has one signal, right? So okay, this one here. Oops. And then this one should be here, because this is a reference. Reference is omega d, not omega d dot. I mean the desired. And for the sine wave, let me see. Frequencies like 1 Hertz, so 6.28 radian per second. Amplitude is just 1. Okay, let's see it. This one y min and y max minus 1. Okay, I think it's good to go. But refresh period should be like 10 second, 10 second. And then let's see the result. Okay, 30 seconds. I need to change simulation time in here. Only up to 10 seconds. And run again. Yeah. If I want to see error, what do? I want to see error. I add another port 1, and this one is minus 0.1 to 0.1. This one also 10 seconds. Error. Where is error? Error is here. Okay. Then I run again. Error 0. Okay. Input is black. Output is green. Because output the same as desired, it means error 0. So you start to build it.